So let me talk about kinetic theory, kinetic model. So this is a chapter 1B, kinetic model. When I say kinetic, what do you think about it? Kinetic model of gas? Motion, right? It moves around. So I can say it has this is a velocity, this is a speed, okay? And this is a velocity. I think that you remember your physics 101. Velocity is a vector quantity, speed is something that is scalar, and then actually we only care about the speed. If you think about it, the gas in this room moves this way, the other way, in every direction, right? Then because of that, what is the average velocity of the gas in this room?
Zero.
It's always zero. They always compensate each other. Is that informative?
No.
There's no information, right? I told you that the gas molecule on average moves like 1,000 miles an hour. And what I mean by this, average like a speed. So the magnitude of the velocity is about that. So it is about, gas is moving, so motion is in the move, and when there's a moving stuff, and gas has a mass, right? So when you have something has a mass and has a velocity, you know what's going to happen? I throw the chalk to you. What you're gonna hit? Well, what it does? This is a kinetic energy turned into a potential energy. So anything that moves with a mass has a kinetic energy. Does it make sense to you? Right? You even remember that kinetic energy? I think we're gonna cover in the general chemistry next week. You even remember this? You guys remember that, right? So that's a kinetic energy, and this is going to be related. So we're going to get back to you. And the overview, before I go to the details, we are going to talk about Maxwell-Boltzmann distribution. So I'm going to use a distribution this way. And the Maxwell-Boltzmann distribution, I'm going to say very quickly about this. Micro P-Chem, I think that Jerry Konowski will go more in depth. And what this Maxwell-Boltzmann distribution is essentially speed distribution. This is what I'm going to say today. Okay? And then essentially what I'm showing to you is actual distribution of speed. So probability for you to find the speed has this kind of the distribution. That's really the nutshell that I want to talk about here. Okay? But I'm going to start with the P. What's the meaning of pressure? And I'm going to start with this, but essentially the important portion is the one that I want to say is this one. Okay. So what this figure graph that I'm going to, I guess, draw one more time is this is a speed of the gas, and that's a probability to find the gas with that speed has this distribution. So this is a wrong statement. The gas in this room moves at the same speed. And that's not true. Okay? Some gas move faster, some gas move slower, and it has a distribution of that speed. And so from here, I need to calculate what is our average speed. And so this from the distribution, I'm going to put a quote on average speed. Because there are different types of average, and you need to get used to those terminologies that you want to say today. And have you also heard about mean free path we call lambda. Okay. So this is actually quite important concept. When gas molecule moves and there's other gas molecules around, right? What is the average distance the gas between the collision? So gas move here, and then if there is enough gas in this room, they collide each other, they make another collision, they make another collision. Right? And what is the average distance between the two collisions? That's a mean free path, and this is a very important concept for somebody who's studying the vacuum science. Do you know who's studying the vacuum science? A lot of people. Have you, I don't know, you are not material science major, right? If you go to material science room, there is a whole, a lot of metal pipes with the pumps. They really trying to get down the pressure as low as possible because they want to control an injection flow of the gas to, you want to modify a surface by shining the array of beams of gas or ionic species. Once they leave, you want to hit it, right? If this thing is happening, then you have no control of the path of the gas, right? It's like throwing the baseball. You want to hit that surface that you target, but if you have a lot of baseball in this room, when you throw it, they deflect, and then you lose your objective. And this one is actually very key to the surface science, which is a semiconductor. Conductor business, like chemical vapor depositions, physical vapor depositions, and all this technique is rely on this understanding. Okay. So let's just start with. Okay, the kinetic theory model. Okay, so now the first one, B1, kinetic theory. And then I'm going to draw this picture. So this is a situation, you have a gas molecule. They're going to collide this way. Okay. So with each collision, there is a momentum transfer. So I'm going to say this direction is they move as x velocity, and this is their momentum. And then when they come out, it is an elastic collision, so it goes to the other way. Okay. So the momentum change here, delta momentum, is 2 times mvx per collision. And why am I interested in momentum? Sometimes people use a P as a momentum. Do you remember your freshman chemistry? The P, the wave number, or the matter wave, and stuff like that. Because the momentum P is a small p. There's so many symbols. The small p momentum is mv, right? And if I do the dt dp, what do you have? dt d mv. What's that corresponding to? Because I'm rarely care about the momentum change. And then you do the time derivative. You know what that is? M? Am I right? Acceleration. I think that everyone should know this equation, right? That's a force. So I kind of, if I know this, so each collision, how much of the momentum changes, and so I'm going to define as for a given time period called the delta t, and then for that, how much of the force being changed, and then I can, how much of the force being generated per collision, and then I know the area of this box, right? Area of this box, and then I can calculate the pressure, right? So that's really the how I'm going. So if I'm going to do one by one, so this is a 4 delta t interval. This is a delta t interval, and then we are talking about the certain volume. So this, they can move. So this is a cross-sectional area. So think about it. For this much of the distance they can move. What I mean by this is Vx times delta t. That's the, like how much distance they can move in this box, and the area is an A. So what that means is A times Vx times delta t is a volume. It defines a volume for a given time interval delta t. So we are talking about gas molecule of that kind of sliced volume that all can collide onto these surfaces. So delta t. Does it make sense? Yes.
So A is the area of the cross
Yeah,
section.
area of the cross section on the other side. So this is an area. A is an area. So it's almost like this is an area. If this is an area, and there is a volume here, the gas molecule moves around, and I'm looking at how much distance they can move. That's a velocity in x direction. Multiply for time interval. So this size of the volume, and with multiplying the total cross-sectional area, that's the volume that these gases can all hit to the other side. Okay? So that's the volume. And then it's an area. And then I want to define the density of particle. Density is n times Avogadro's number divided by. So this is a number of particles per unit volume. Okay? So that is something that I can say, because in this one we have n is my number of moles, and the total volume in this system is total volume is V, and so that's the density of the particle. And like I said, there's a momentum change is this much. And then if I have this, there are equal opportunity going forward and backward. So I'm considering only the half, which is let's say right side collision. So I'm going to break up all these terms that I just said. And so let's make it into an equation. So what I want to do now is I want to see the overall momentum change for the system. My system is with a volume with an n, and this is where I am going, and then I'm going to do. Okay, so this is really the key part. I want to know momentum change in delta t. So then I have to say, okay, area Vx of delta t. This is an actual, the slice of the volume. This is like a slice of the volume shown in that shade. And will collide, but with that among the volume, this is the probability for you to find out. So this is an actual density, right? So by multiplying together, you will see essentially simply number of gas molecules colliding either side of the wall. Okay, and then what? And I only consider only half of them multiplying. So this is just for me, just to bookkeeping. I'm looking at only one side of the wall, how many gas molecules they are colliding it, and for each one, what is the number? 2m dx. Right? That's the actual momentum change in the x direction. Right? I'm going to put everything. And then what did I say about this momentum change? 2, the rate of momentum change. Do you remember this? This is like a delta P. The rate means what? Delta P divided by delta T. And do you know what this related to? Force, right? Force, right? Delta or dmv divided by dt ma is an F. This is what you have to recall. But I'm getting here. I want to know the force defined by momentum change of this many gases hitting the right side of the wall. That's it. So, and it's a lot of things, but it just comes down to this equation now, which is a volume m, and then okay. Something. Okay, so I'm going to use this one to the front. So I'm going to say N, A, getting there, A, Vx,